Hello, welcome to the second of our treatments of spatially constrained clustering. This time we focus on three specific methods that implement the spatial constraints in hierarchical clustering. And the three methods are spatially constrained hierarchical clustering. It's very straightforward implementation of a constrained clustering method. And the other two are a little more specialized and known by the acronym of SCADR and Redcap. We begin with spatially constrained hierarchical clustering. And the principle is very simple. It's an agglomerative clustering procedure with a constraint imposed. As we've seen earlier, we can impose constraints such as a minimum population or another minimum size. But in this case, the constraint is spatial. So what does it mean? When we merge two observations as we climb up in the tree, in the dendrogram, we can only merge entities that are contiguous. And then as we do this, the contiguity relations have to be updated because, let's say, A and B are merged together and B is contiguous to C, but A is not, then this has to be updated in the spatial weights matrix. So every time two units that are contiguous are merged, the distance matrix shrinks by 1 unit, but also the spatial weights matrix shrinks by 1 unit. So this dynamic updating of the spatial weights is something implemented in GeoDa. And so then, in terms of the linkage methods, the linkage functions, we have the same options as for standard hierarchical clustering. So we have single linkage, full complete linkage, average linkage, and Ward's method, which is by far, as we've seen, the preferred method. So to illustrate this, I will be using a different example this time. I will be using the counties of Arizona, and that's because Arizona only has 14 counties, so it's really straightforward to illustrate it. And here's the map of the counties, and the graph is a connectivity graph. It shows the counties that are connected by queen contiguity. So that's our basic weights matrix, and then we have the variable of interest, and you have the details in the notebook as usual, is unemployment rate, and we can compute the distances between the counties in terms of the unemployment rate, and that's the 14 by 14 distance matrix that results. Now the difference with the standard approach is that now we limit the units that can be combined to those that are contiguous. And for example, County 1 is contiguous to 5, 6, and 10. And here's County 1 connected to 10, 5, and 6. And so to make this explicit, only those cells in the weights matrix that correspond to pairs that are also spatially contiguous are marked in red. So we search over the red ones and we find the two that are closest together, and this happens to be 8 and 14. Closest together in terms of the variable distance, and also closest together in terms of satisfying the contiguity constraint. So then we put 8 and 14 together, and then we continue in the usual fashion. In the next step, we merge 9 with 8 and 14. 9 is also contiguous to 8 and 14. So we see 8, 14, 9. And this is an example of the updating of the weights matrix, because 9 is not a neighbor of 8. 9 is only a neighbor of 14. But as 8 and 14 are merged, the neighbor set is reconstructed, or actually updated, to contain the neighbors of the full cell now. And as always in hierarchical clustering, once two units are combined, they are never separated again. So it's easy to update the weights matrix in that respect. So this is the same kind of dendrogram that we get in the standard hierarchical clustering procedure, except that each time now only contiguous units are being put together. And we can put our cut at any value of k, as we could do before. In this example, we have 4 regions, 4 clusters. These 5 counties, then the next large group of counties, and then 2 singletons, 10 and 1. And in the map, it looks like this. So we use hierarchical clustering. That means that we build a dendrogram. We put together entities that are the closest together and also contiguous. And in the process of merging units into larger regions, we have to update the weights matrix, the spatial weights matrix. We have to update the contiguity relationships to make sure that they reflect the new combinations. But that's really all there is to it, and we can implement this relatively straightforwardly for any of our common linkage methods. This is the point of departure, and I just want to show this to illustrate how a standard hierarchical linking using Ward's criterion for k equals 6 gives a result that is anything but contiguous. And also, just as a frame of reference, we see the ratio here is 0.53. Okay, now let's look at Ward's, the same criterion. The measure of fit drops to 0.46. So that, in a sense, is the price we have to pay for imposing a constraint. An unconstrained solution will always have a better value than a constrained solution. That's just the nature of constraining. So only if the constraint is not really a constraint will we get the same result. So if the initial result was already contiguous, then it doesn't make any difference. But typically that will not be the case, as in our example, it's clearly not the case. So therefore we pay a price for imposing the constraint in terms of a lesser goodness of fit. And here in this example, we see 4 very nicely formed regions and then 2 singletons. So as we go just very quickly to some of the other linkage methods, this uses single linkage, just as before, pretty lousy results, 5 singletons and then everything else together, not very good clustering. Same for average clustering, average linkage. We get, again, 5 singletons and then 1 large one. Complete clustering is a little bit better, but we still have 3 singletons, 2 fairly small regions, and then 1 very large region, in contrast to what we saw with Ward's method. So, spatially constrained hierarchical clustering, very easy to implement. The only tricky part in terms of the implementation is a dynamic updating of the spatial weights, but that's implemented efficiently in GeoDa. Okay. Then the 2 more specialized methods. The first one, and very often used one, is SCATER, and SCATER stands for, believe it or not, Spatial Cluster Analysis by Tree Edge Removal, where cluster is spelled with a K. It was proposed in a paper by Asuncao and co-workers in 2006. And the idea is very clever. It uses the weights matrix or adjacency graph. We've already seen this in a number of other contexts as well, specifically in spectral clustering. So we take the adjacency graph as a representation of the connectivity structure and make it a weighted graph where the weight of each of the edge, so each observation is a node, the connections between the contiguous observations are the edges in the graph, and then the weight of that edge is the distance and attribute space between the 2 nodes that are connected. So instead of having real distance, geographical distance, as we had in the context of spatial weights, now we make it attribute distance, as in most of these clustering techniques. So the attribute distance between 2 nodes is the weight of the edge, and then the algorithm, the scatter algorithm, reduces the full tree to a minimum spanning tree, which is kind of a summary of the essential features of the tree, and I'll talk a little bit more about that in a few minutes. And then it figures out an optimal way of pruning the tree. And you can think of, just as we did when we discussed spectral clustering, we can think of each subcluster as a set of connected nodes that are then separated from the other nodes. So to have k clusters, we have to make k minus 1 cuts in the edges of the tree. And that's basically the logic behind the scatter algorithm. In contrast to the previous one, which was agglomerative, bottom-up, this one is top-down, is a divisive hierarchical clustering approach. So we start with everything being together in one cluster, so to speak, and then we make a cut so that the resulting two units are as different from each other as possible, or in other words, we try to minimize the dissimilarity internally in each of the clusters, maximize the similarity in each of the clusters. So these are all familiar concepts by now. Let me just go quickly over some graph terminology. We've seen this before. This is just a refresher. We have the graph represented by G. The nodes are V, or vertices are V. The links or edges are L. And then within the graph, such as a connectivity graph, we can define a path. And a path is any sequence of nodes connected by edges. And then there's some special paths that we'll see in a second. So, as I mentioned, the network connectivity is based on the adjacency. The value of the edges is the attribute difference between the two nodes that are connected by the edge, and the objective is always the same one: minimize within group dissimilarity. So, returning to this concept of a path, a spanning tree is a tree made up by a unique path that connects any one of every node is connected, and there are n-1 edges. So there is just a way through all the nodes that hits each of them once and cuts the number of edges from potentially n squared minus n, if the tree is fully connected, to n-1. So that is the real power of making a spanning tree. And then a particular type of spanning tree is the so-called minimum spanning tree, or MST. That's a spanning tree that, as the term says, minimizes a criterion. And specifically in our context, it will minimize the sum of the distances between the nodes, which is the sum of the dissimilarities between the nodes. So we can construct a minimum spanning tree using a number of different algorithms. The most common, and also one of the oldest, is Prim's algorithm, which basically moves through the tree sequentially and finds the shortest path, so to speak, that connects each node so that we have exactly n-1 edges. So that minimum spanning tree can be constructed, and then we have to prune the tree. We have to essentially cut it in pieces so that the end result gives us the desired number of clusters. To illustrate this, again, we're going to use the same example for the counties in Arizona. On the left is the original map with the connectivity graph, and on the right is the minimum spanning tree. As you see, each node is visited by the spanning tree. There are exactly 13 edges, which is one less than 14, the number of nodes. And we're going to figure out how and where we make a cut in this tree. And we want to make the cut so that the total sum of squares, which is always the same criterion, is minimized, it drops the most. Because in contrast to agglomerative clustering, where we start at the bottom, where the total sum of squares is 0 because each cluster is a singleton, so there's no differences there whatsoever. And as you move up in the tree, it gets worse, so to speak, and the total sum of squares increases. Here is the other way around. You start at the top with the maximum sum of squares, the total sum of squares. Once you cut it in two, each part has a smaller internal sum of squares. So this criterion of the sum of all the dissimilarities starts to go down, starts to decrease. And so in the logic of the scalar algorithm, where we cut is where we get the greatest improvement in this respect. So we prune the tree and we consider finding the spatially contiguous clusters as the result of a tree partitioning or tree pruning problem. And as I mentioned before, if we want k clusters, we have to remove or cut k-1 edges. And we do this. It's a greedy algorithm. Again, it tries to make the biggest improvement each step. So this is the total sum of squares that we have to start with. So in the beginning, that is just the total sum of squares. And this is the sum of the sum of squares internally to each subtree. So we start with the full tree, we make a cut. This gives us two subgraphs or subtrees, and within each of these we can compute the sum of squares, and the cut that gives the biggest decrease in this criterion is the cut that we want to implement. And then, of course, we repeat the process. We go to each of these subtrees, and then in that subtree, decide which cut gives us the most improvement. And let me illustrate this in our example. So, in the beginning, the sum of square deviations is 13, one less than 14, and we can consider every possible cut. So this is a cut between 1 and 10, this is a cut between 2 and 6, 2 and 11, and so forth. In each of these cuts, we end up with subtrees. And the one subtree in this case of this cut, if I go back here, so if we cut between 1 and 10, then 1 is alone and 10 is everything else. So when 1 is alone, the corresponding sum of squares will be 0. So this is a singleton, and this is the sum of squares of the rest. The difference between what we start with is the 13, what we end up with is the 4.89, is 8.1. And we repeat this and have to recalculate this for each of these possible cuts, which is actually a bit of a drawback because that's a very involved process. And so we see how much we improve for each of these possible cuts, and we find that for the cut between 5 and 10, we go down by 9.8, which is the biggest improvement. So our first cut is between 5 and 10. So this disappears. So then we have two subtrees, the one with 10 and 1 and the one with everything else. So obviously the cut in this subtree would be between 10 and 1. In the other subtree, we have to evaluate all the possible pairs. And in this table, you see the result. In the first cut between 1 and 10, they both become singletons, which then gives us the decrease is equal to the initial total sum of squares. And these are all the other cuts that we can consider. And the cut between 8 and 11 is the largest one. And we can already quickly see that the next cut is going to be between 1 and 10 because none of these improvements comes close to that. So you can't do any better than that. So that's in fact what we get. So the first cut was here, the second cut is here, the third cut will be here, and this gives us, as a result, the cluster, the 4 clusters, each consisting of it's a very similar result to hierarchical clustering, but slightly different. There's a few differences. So this is how Skater works. The key is to reduce the graph of the adjacencies to a minimum spanning tree, and then apply a divisive hierarchical clustering process where we move down the tree, so to speak, by applying the optimal cut in each stage. So what does this look like for our Gary example? And this is to illustrate one of the downsides, actually, of the Skater algorithm. It's very easy to implement. It works really well. It's a little bit slow to calculate for large problems. But the major drawback is that it's a hierarchical process, and just like, as I mentioned before, if you go bottom up, once 2 units have been put together, they cannot be separated anymore. And the opposite holds in this case. Once 2 units have been split, they cannot be put together anymore in any other way. So here we start with 4 regions, and if we go to 6, you can notice that essentially this region 4, the green one, is split into 2, and similar, the one in the middle here is also split into 2. This is the hierarchical nature of the pruning. You cannot have that one of the units in here, for example, would become part of the green one, or any other swapping is not possible. So once you're split forever. So the issues with this approach is that obviously by going to the minimum spanning tree, you remove some possibilities, and the solution space is constrained. We'll see that in the partitioning methods that we'll consider later, that is not the case. There's no constraining of the solution space. And then also by the nature of the constrained solution space, we only have cuts in the minimum spanning tree and subsets of the minimum spanning tree. So it's a divisive process. Once you cut, you cannot be put together, which ends up giving us local optima, not necessarily a global optimum. And as I mentioned, since these internal sum of squares need to be recalculated for every possible cut, this doesn't scale that well. It can be made more efficient, but in essence, for very large data sets, it's a bit of a challenge. Okay. And finally, Redcap. And Redcap, as it turns out, combines features from both the spatially constrained hierarchical clustering and from the logic behind Skater. Redcap stands for, again, something pretty complicated: regionalization with dynamically constrained agglomerative clustering and partitioning. And it was proposed in a number of papers by Guo. And as I mentioned, it combines the idea of 2. It's both agglomerative, bottom-up, and divisive, top-down. In essence, what it does is it takes the idea of spatially constrained clustering to move bottom-up, and then the idea of Skater to go back down. And Redcap is not one method. It's actually a family of algorithms, and they are classified on 2 dimensions. And one dimension is whether they keep a fixed contiguity relation, as is the case in Skater. Once you have the minimum spanning tree, nothing gets updated. Everything stays the same, versus an updated contiguity relationship, which we had in the first method in the spatially constrained hierarchical clustering. The weights were updated. And the fixed method is called first order. The updating method is called full order in the Redcap terminology. And then tacked on to that dimension, we have all the linkage functions: single, average, complete, wards. And so we have every combination first order single linkage is actually identical to scatter. We have first order average and so on, and the same for the full order. So there are about 8 different algorithms in GeoDa implemented under the Redcap label. They differ between fixed contiguity and flexible updated contiguity, and they differ in terms of the linkage method, just like we had with the spatially constrained hierarchical clustering. So, as I mentioned, it's a combination of 2 ideas. The first idea creates a dendrogram for the spatially constrained hierarchical clustering, the same as we've done before. And then it turns that dendrogram into a minimum spanning tree. And this is actually a property, a graph theoretic property, that a dendrogram can always is an alternative representation of a minimum spanning tree. So once we have our minimum spanning tree, then we're in the same game as with scatter, and we apply the cuts in exactly the same way. So that's the general principle behind Redcap. And let me illustrate this again with our Arizona example. You may recognize this as the clustering dendrogram in spatially constrained hierarchical clustering. So first we put 8 and 14 together, then we tack 9 onto that, then we put 2 and 13 together, and so on as we move up in the graph in this direction. The minimum spanning tree that corresponds to this is given in this graph. And I have these little blue labeled numbers besides each edge to show you at what step in the dendrogram they are put together. So as we saw, 8 and 14 are put together first, then 9 is tacked on to 8 and 14, then 13 and 2 are put together, then 12 and 4 are put together, and so on. So by going through the dendrogram, and again, the extensive details are in the lab notes, by going through the dendrogram, we turn it into a minimum spanning tree. And this looks exactly the same as the scatter. We have our edge lengths are the multi-attribute dissimilarities between the 2 nodes that are connected, and we cut and prune, and we end up with our clusters. And in our little toy example, these are very similar to scatter. I think there's one difference. So Redcap is a family of methods distinguished between not updating the weights and updating the weights. Actually, the ones that don't update the weights are inferior, so we don't actually consider them. But then they differ in terms of the linkage methods. And we can, again, just for illustration purposes, this is the result of Redcap using Ward's method with updated weights. So this is the full order Ward method. And you may recall, or you may check, that this looks very similar to the result of spatially constrained hierarchical clustering. We again have some singletons, but there are tiny differences between the number of clusters in the first 3 groups. So a few departments are allocated with a different cluster. In yellow, you see the minimum spanning tree that is constructed from the dendrogram, and then you can also see where the cuts are made. So that's a way to see how the structure of the clusters comes into being by means of the different cuts. So for example, here is the cut between cluster number 1, which is the light blue one, and cluster number 4. Here's the cut between 4 and 3. Here's the cut between 3 and 2. And then, of course, for the singletons, we have also a cut. So this is, in a nutshell, how it works. Just for completeness sake, single linkage is actually a fairly nice result compared to the simple spatially constrained hierarchical clustering. Only 1 singleton and several reasonable sized regions. This is the average linkage, and then this is the complete linkage. So what have we done now? We have treated presented three different methods. One is actually a family of methods that impose the contiguity constraint in a hierarchical clustering algorithm. And the result of this is a set of regions that are not only internally the most cohesive we can get, but are also spatially contiguous. And as a price for that, for imposing this contiguity, the overall fit of the clusters decreases a bit. Okay, so the next and the final set of slides will consider how we put spatial constraints in partitioning methods. See you then.